All right, good afternoon, everyone. Can you hear me back there? Good afternoon and welcome to the ICS seminar. I am Pavlos Protopapas. I am the scientific director for the ICS. And I'm about to introduce our speaker because before I introduce our speaker, I have a couple of things to say. We have 7 talks scheduled for this semester. We cover topics in data science. We have 2 speakers from industry, and the rest are faculty in different places. Mainly, we have 3 speakers this year from the Harvard campus, 4 actually, who are new faculty here, so we decided to be the first ones to hear them. I hope you enjoy the lunch. We're going to be having lunches every seminar. And it's a variety. Sometimes it's burrito, sometimes it's pizza, something. So come. So next week, we have another talk. Is Thomas Gwen from Square, the little Square you see everywhere and you pay. He will be here talking about data science they're doing there. So it is my pleasure to introduce our speaker today, Michael Franklin. For the students, you should know him. If you don't know his name, you will know it next semester when you do CS205. He's one of the authors. He was the director of the lab that started Sparks. So you know a lot about it next semester. Michael is a faculty at the University of Chicago. He's the Liew Family Chair of Computer Science. He's leading the effort there to create a data science program. He has a lot on his plate, and he's creating everything related to data science in University of Chicago. You can ask him questions after the talk if you want to. Before that, he was 17 years at Berkeley. 17. There he was at the professor of computer science and chair of the computer science division. He got his PhD in computer science at the University of Wisconsin. Then he went as a junior faculty at College Park, Maryland. And then from there to Berkeley, and then from Berkeley now a year ago to University of Chicago. When he was at Berkeley, he had 2 years off, as everybody in the Bay Area starting a company, but we're not going to talk about that so much. Today, he's, as a first speaker, he's talking about big data software. What's next? Hyper big software. And please.
Huge data.
Please, let's welcome Michael.
All right. Well, thanks, Pavlos, and thanks for the invitation. And it's exciting to be here and for the first seminar of the series. One of the reasons I came here was because I wanted to learn about what you guys are doing in data science, and so I'm hoping we get a chance to talk afterwards. But as part of my admission to getting in here, I needed to talk to you about a few things. So I'm going to, this is a talk I gave to, as a keynote at a database conference actually last week, the VLDB conference. And I've tried to kind of de-database it a little bit, but you'll still see some of that in there. So my background is in database management and so on. And so I know it's an audience with pretty diverse interests, so don't hesitate to, stop me or ask a question or whatever if I'm talking about things that don't make sense to you or you just have something you want to bring up. So yeah, so it's one of these kind of vague titles where, when they ask you for an abstract and you're not sure what you're going to talk about, that you can come up with. So what I'm really going to do is tell you probably about half the talk I want to kind of walk through kind of the evolution of the Spark system that Pavlos mentioned as an example of a big data platform. And then the second half, I'll try to be a little more forward-looking, still focused on a bunch of things that we were doing in that project, but kind of where I think some of the big research challenges are, in the area of big data software. So just by way of introduction, databases is a funny field. It's, when I got into it, it was kind of the course that people would take when the AI class filled up. It was never kind of viewed as one of the cutting edge areas, at least in research computer science. But as data has gotten more and more important, the whole data management field has exploded. And where we are now is, it's just a wonderful place to be doing research, because we've got this kind of push and pull of change going on, where, underneath, kind of at the hardware level, there's just tremendous changes happening. So there's, kind of new breakthroughs in memory technology and storage technology. So, non-volatile memories of all different shapes and sizes that are really changing kind of fundamental underlying assumptions of where the bottlenecks are in data processing and so on. New types of processors, so it's not just CPUs anymore. You can work with GPUs, you can work with FPGAs, you can work with TPUs, you can work with multi-core systems that have very different types of processes in them. And so kind of the entire bedrock on which data management technology had been developed over 40 years is really fundamentally changing. And so that obviously raises a lot of new interesting research problems. So that's kind of on the bottom. On the top, as I mentioned, data is kind of everywhere. And the types of applications that people are doing and the requirements of those applications has also been expanding and changing dramatically. And so that's causing a rethinking of data management architecture, from kind of as a user pull. So you get both the technology push from the bottom and the user pull from the top. And that basically means we get to rethink everything in data management. So that's a great opportunity for research. This is kind of the obligatory big data slide. I give talks with the term big data in it. Basically, it used to be really hard to collect data. It used to be really expensive and difficult for lots of reasons. And in many applications now, many domains, that's just not true anymore. It's becoming increasingly easy, increasingly cheap to collect lots of data. And the challenge really is, trying to figure out what's in there and how do you make use of it? How do you gain insight from all that raw data that you're collecting? And I don't have to tell you, this is happening like on a college campus. It's basically everywhere. And so that's kind of what's driving things from the top in terms of innovation. So I'm going to talk a lot about this system called Spark. It's now called Apache Spark because we donated it to the Apache Software Foundation. I think a lot of people here already know about it. It's a big data processing platform. I'll give you actually a few details on it in a second. This is just my one slide that, if you don't know about it, is meant to show that it's got a lot of traction. And so, there's meetup.com is a place where people can register, groups that meet periodically about different topics. And in 2012, the end of 2012, the graduate students in our group at Berkeley, when I was still there, set up the first meetup group for Spark in San Francisco, and had a few dozen people in it. I checked it this morning, and currently there are 622 groups around the world where people, instead of going home to their families or to watch TV after a long day at work, actually go and sit and talk about Spark. And yeah, I know it's a little hard to believe, but so that's just kind of one unscientific measure of kind of the impact that we've been having. And I could talk more about that if you have questions. But the broader context is really this explosion of open source software that happened. And let me just build this out. Starting kind of in the mid part of the previous decade. So, big web companies, or companies that were going to become big web companies, sort of figured out pretty early on that they were going to be analyzing lots and lots of data. They're going to be collecting lots of data from a bunch of different places. And they felt, either rightly or wrongly, that the existing commercial database technology was not going to serve their needs. So either it was not going to scale to the size of data and the number of machines that they had to process on, or even if it could scale, it was going to be too expensive for them. And so they started building a lot of their own software. And initially, this software was proprietary. So a lot of it happened, say, at Google in particular. And they built an engine called MapReduce, which is really a fairly low-level engine that lets you specify programs that can scale out. So what scale out means is, if you've got a computation or an analysis that you're doing on a certain amount of data, and you get more data, you should be able to add more computing and storage resources of sort of equivalent magnitude and still be able to answer the same question over more data in the same time. So as you're adding more and more data, you just add more resources and you can still get your job done. And so MapReduce was a very nice way of getting scale-out computing for certain computations. And at some point, there's a group of people that were trying to build a search engine. And they realized they needed a MapReduce type of technology. That technology was locked up, as a proprietary system at Google. And so they decided to build their own, and they built this thing called Hadoop. And Hadoop has two main components to it. One is a MapReduce engine, which does this parallel programming. And the other is a very scalable storage system called the Hadoop file system that basically has that property of just being able to add more and more storage as you're getting more and more data. And so in 2006, Hadoop was released as an open source project. And that started this explosion of innovation in the open source community. And this only goes up to 2013. But it just keeps going and going, and there's more and more systems. It seems every day, certainly every week, there's a new announcement of an open source big data processing tool. And so, again, started 2006, and it's been expanding there. The context for this talk, just quickly, so at Berkeley, while this was happening, there was a project called the Rad Lab, which was focused on building basically self-managing computers. And the insight that those guys had was that to build a self-managing computing system, you'd need cutting-edge machine learning technology. And so they put together a group of really good computer systems people and really good machine learning people. They got them all to sit in the same room, and they got them to work together for 5 years on solving this problem of what was called autonomic computing. For the purpose of this story, what was interesting about that is I think it was one of the first instances that I'm aware of where people from machine learning and computer systems really worked together in a deep collaboration over a long period of time. And so towards the end of that project, something very interesting happened. Some of the machine learning students were trying to run some models on Hadoop, and they were getting really bad performance. And they worked with systems people, so they went over to systems people and said, hey, can you help us figure out what we're doing wrong with Hadoop? It's we're trying to, they were doing logistic regressions, and this is iterative model building. And it was just running incredibly slow. And they said, can you help us debug our program? And the systems folks looked at the program and said, no, you're not doing anything wrong. This is just the way Hadoop operates when you're doing iterative programs. And those students took a step back and they said, hey, well, maybe we can build a MapReduce type system that works well for these types of machine learning applications. And that was the genesis of this system called Spark. And so that actually started around 2009, and the first paper came out in 2010. When the Rad Lab finished, it was a 5-year project. We realized that this big data wave was about to hit, and that we had this unique resource of systems and machine learning people who knew how to work together. And so we said, okay, let's not break up the band. Let's just kind of refocus what we're doing. And we created a new project called the AMP Lab, which was focused on big data analytics. And so the way I like to think about it is for the Rad Lab, for the autonomic computing, the machine learning people were kind of working for the systems people in some sense. And what we wanted to do in the AMP Lab was flip that, so that the systems people were helping the machine learning folks figure out how to do scalable machine learning. And that was a 6-year project, and I'll tell you about that next. But that's kind of the background for the talk. The other thing, I guess, before I get off this slide is important. One thing you should realize is this is really fun if you're a software developer, because you can create a new system and put it out in the open source and get some traction. If you're a practitioner who's really trying to solve a big data problem, this is a nightmare because there's new systems coming all the time. They're incompatible. They're at widely varying degrees of maturity. Some are going to survive, some won't. And you have to navigate your way through this morass to figure out how to pull all those pieces together. And so that's going to be a big part of the story, too. So just remember, and this goes, this would hit the ceiling if I built it out to today. All right. So let me tell you just one slide on the AMP lab. So AMP stands for Algorithms, Machines, and People. The idea was that's what you have to, those are your resources for making sense of big data. So for algorithms, we're thinking machine learning, business intelligence types of processing. For machines, we're thinking about cluster computing and cloud, elastic cloud computing. And for people, our focus was on crowdsourcing and human computation. And the challenge that we set up was, could we build a system that integrated these three very different types of resources in a way so that when somebody wanted to solve a big data problem, they could mix and match, the right pieces. So, you run your machine learning on some scalable system, and for the parts that the machine learning algorithm can't do very well, you're able to call out to the crowd and get some human input. And that's what we tried to build. So it was a 6-year project. It was a pretty big project. There were about 12 faculty involved over the 6 years, really 4 or 5 core faculty, about 120 PhDs and postdocs. Went through that, and some are still finishing up, and including a bunch of really good people we got from Harvard, and they're all doing well. In addition to the systems and machine learning, we also had a large database component. That was my involvement and my group's involvement. So pretty big project. It was funded by an NSF Expeditions Award, which is a nice 5-year award that NSF will give to ambitious projects. But more interestingly, it was also a collaboration with, over the 6 years, about 40 companies. And in fact, about half our funding came from the companies, half came from the federal government. But more important than the funding is we got very early access to potential users for our software. And so early versions of Spark were being used at places like Facebook and Yahoo and Microsoft and so on, Amazon, very early on. And those people were giving our students a lot of really good feedback on what worked and what didn't and what they would like to see. And so it was a great collaboration of public-private partnership, if you will. So that was a big deal. Because we spanned all these areas, I don't know if these acronyms mean much to everybody, but we were basically able to publish in the best database places, the best operating systems places, the best machine learning places, and as far as I know, the only human computation place. And so, we covered this large intellectual range. And then just some statistics. 3 ACM dissertation awards, if you're not familiar with that. That's an award given to the best PhD thesis in the world in computer science each year. Best for some definition of best. So we won one of those and 2 honorable mentions. We got some high-profile invitations to the CACM Research Highlights, which is, again, one of these things where they pick one paper from across computer science to show to the broader community. We've had 4 direct spin-out companies have raised almost $500 million of venture capital, so there's a lot of commercial interest, as well as a lot of products that because we do everything in the open source, a lot of companies have kind of just taken our software and are reselling it in various ways. And then, 3 marriages, which, yeah, okay, so good. So that's the AMP Lab. So what we did at the AMP Lab is we built this stack called the Berkeley Data Analytics Stack, right? So this is, the abbreviation is BDAS, and we like to pronounce it badass. And, you kind of have to read this bottom up. But at the very low level is a system called Mesos that lets you take a large physical computing cluster and break it into individual virtual clusters. We had some storage software that we built that would abstract, kind of do the same thing for distributed storage. And then, we had 2 processing engines that I'll talk about both of these, Spark and Clipper. So I'll skip that. And then the interesting thing here is all the different systems that would sit on top of those engines that would allow you to process data in different ways. And so you'll see there's a relational query processor, there's a graph algorithm, there's a bunch of machine learning stuff, there's a streaming system, there's a way to run R programs if you want to do statistical processing. So all those things were layered on top of this stack. And then all of this was driven by applications that we were able to find around the Berkeley campus, things like genomics. We did a lot of work with cosmologists on campus, different Internet of Things types of applications. And you know, again, you got to keep in mind that this is an academic research project. So, you know, each of these white boxes was somebody's PhD thesis, and maybe, you know, a few different people's PhD thesis came out of there. But we were able to get all of this software working together, and everything I'm showing here, you know, is released and available as open source software that you can download and use. There's a bunch of stuff we did that isn't here, and that's how research works. Okay, so that's the context. Great. So, you know, take a step back. You know, one of the things I think was most interesting from a computer science point of view of what we were able to do in the AMP lab was this ability to bring people from very disparate parts of the computer science domain together to collaborate on this project. And so, you know, it's this interesting confluence of these different ways of thinking. And, you know, it sounds like it might be easy, but it's not. You know, people come from very different traditions and focus on very different types of problems. You know, one of the things that's part of the backstory for this is when Hadoop and MapReduce started getting really popular, there was a big backlash in the database community where, you know, people looked at that technology and said, well, you know, first of all, it's really low level. It's a big step backwards in terms of how you program it. It's missing tons of features that have been developed over you know, decades of database development. And it's not really anything new. We've been doing parallel databases for years and years and years. And so, you know, there was a lot of concern in the database community that you know, this kind of new technology was somehow not, you know, was getting more credit than it deserved. And I kind of took this part out of the talk, but my view on what happened there is that, you know, in a sense, what was going on was that Hadoop and MapReduce were kind of classic examples of disruptive technology, or, you know, what they call now disruptive innovation, where, you know, there's a bunch of incumbents, in this case the database companies, who had been, you know, servicing, you know, the mainstream market, and they're adding to their products, they're innovating, and they're basically heading towards like this ultra high performance, ultra sophisticated use case, because that's where you have to go. And you know, a new competitor can come in with much less functionality, doesn't even work as well, and actually start meeting the needs of the mainstream in some ways better than the incumbents can. And I believe that that's what happened, or that is what's happening really with a lot of this big data software technology. So that's really what I want to talk about is kind of, you know, there was this base idea of scale out parallel computing that was popularized by MapReduce and Hadoop. And how did we go from that to something that actually is a much more functional, much more useful class of software? And I apologize in advance. I'm really mostly going to talk about Spark, because that's what I know and that's what we've worked on. But there's been lots and lots of systems that have been built, and I'll mention some of them along the way.
Wasn't the open source aspect of Hadoop equally important? I mean, in its ability to disrupt, it was more accessible to people who wanted to do something new and different with their data than the database systems?
Great question. So the question, if you couldn't hear it in the back, was, wasn't the open source nature of Hadoop one of the big reasons it was disruptive? And absolutely it was, but there were also existing open source relational database systems. There was MySQL, which was quite popular. There was Postgres that was quite popular. And so it wasn't just the open source that made it take off that way.
It required more structured and static data.
Oh, now you're giving my talk. That's exactly exactly where we're going. Yeah, good. Okay. All right, good. So, okay, so along the lines of the question, so, my pitch to you is, there was this interesting technology that was developed, but it was lacking in a lot of things that people had come to expect a mature database system to be able to do. And so, my argument is that over the years, the 10 years or more, a bunch of those database ideas have now worked their way into the big data software stack. Okay, and so what are the kinds of things that are important? So I call this database thinking, just because I couldn't come up with a better name for it. But so a couple things are really important. In relational databases, one of the big ideas there was that you should specify when you want to write a query, when you want to ask a question over a big database, you should specify the answer that you want to get, not how to get that answer. Okay? And what that lets you do is it gives you some separation between the actual implementation of all those underlying data structures, all those algorithms that do the processing, and the actual question you're trying to ask, so that as the data changes, as the underlying hardware changes, you don't have to rewrite your program every time. Okay? So it's a classic example of abstraction, as you'd find in any good computer science system. And so the idea is, declarative queries, you say what you want, but not necessarily how to get it done, okay? So that's one of the big ideas. The other one, and I think I've talked to a few people here today about data science and what's different about it. I think this is a really important thing, which is when you're trained as a computer scientist, you typically think about, I'm writing an algorithm to do something. I need to create some data structure, so I'm going to design my data structures to support that algorithm. But that's not how database thinking works. Database thinking, the data is a representation of the real world in some way. And you want to design that so that you can accurately and efficiently and effectively model the real world. And so you think about the data independently of any single application that you might write on the data. Okay? And that has very fundamental impact on how you build your system and how you think about building a larger system. So that's an important database thinking technique that isn't present in a lot of other parts of computer science. Of course, if you're moving lots of data around the system, you have to think hard about storage hierarchies and how to manage it. So those are sort of three key things that if you study database systems that you learn and they sort of become part of your DNA. Okay, and they weren't really in, the original MapReduce and Hadoop because they came from a different tradition. So okay, so good. So how do these things get put into the big data framework? All right, so let's talk about Spark. So that's a picture of Matej Zaharia, who's really the brains behind Spark. He was a main PhD student on the project, and basically, if you remember that picture I showed you of that explosion of open source projects, what was happening there is that people would take MapReduce and they'd say, wow, I really love this idea of being able to scale out my processing, but MapReduce doesn't do what I want it to do. I want to run queries over graphs, and MapReduce isn't very good at that. Or I want to do real-time streaming data, and MapReduce isn't very good at that. And so each of those systems that you saw getting built up over the years was basically an instance of somebody taking that MapReduce framework and specializing it to do something that it hadn't meant to do. And so as we already talked about, that leads to this, real problem for practitioners who need to do multiple functions. And so Spark basically said, okay, rather than every time we see a new problem, create a new system, why don't we see if we can generalize MapReduce? So don't specialize it, but generalize it. Make it a little more powerful, make it a little wider, okay? So we're going to do that. And in order to do that, you have to extend the programming model, so make it do more than map and reduce. And because of this problem I told you about earlier, with Hadoop not being able to perform well for certain types of machine learning applications, that turned out to be a memory management problem, and you need to fix that. So I'll tell you how we do that in a second, but the idea is if you could do that, then you can plug in to the Spark framework, or to whatever framework you build, all these different ways of getting at the data, whether it's relational queries through SQL or graph queries or what have you. Okay, so that's kind of the big picture. So I want to spend basically just a slide on each one of these things. So when we talk about a richer programming model, what do we mean there? So Spark has, I think at this point, about 80 or 90 different primitives that you can call. One of them is map, which is where you apply a function to an individual item. And another one is reduce, where you take multiple items and combine them to come up with a single answer, so if you're trying to do an average or a sum or something like that. And you'll notice if you can do map and reduce, then you have map reduce. So that's where you start. And then you start growing from there. And so this is a subset of some of the different functions you can do with collections in Spark. But I point out these, if you look at them, this is, again, this was from my database talk. This is Ted Codd, the inventor of the relational model. And my point that I was making to my database friends is, you know, Ted Codd would love this stuff. I mean, he invented it. So you can basically just add these relational operators and other operators, you know, into the MapReduce framework to give it more power. So that's what I mean by expanding it. In terms of memory management, here's what was happening with that use case I told you. So what was happening is we were trying to train a model. And so when you train that model, what you do is you read in your data from the file system, you apply map to it, you apply your reduce to it, you get some intermediate answer, you write that out to disk, and then you need to iterate, right? You want to try to improve your model. So in Hadoop, what you do, or Hadoop MapReduce, what you do is you then read the data in again. Okay, remember, the whole point of what we're talking about is big data, right? So that's expensive. You map it, you reduce it, you write out the intermediate result again, you read it in from disk, you read your data in, and so on. And so basically, every iteration of this machine learning algorithm was communicating with the next one through magnetic storage, right? Which is, you know, pretty much the slowest way you can communicate in a modern computer system. So again, apply a little database thinking, or in this case, maybe even systems thinking. And you say, okay, well, what I'm going to do is I'm going to bring stuff into memory, and I'm going to remember that it's there. So I don't have to read it again, especially, you know, if I'm not changing it, especially. And then for these intermediate results, I'm going to be smarter about how I let one part of the program read the memory of another part of the program. So I don't have to write it out to disk into a file and then read it back in. Okay? And that's kind of what Spark, you know, those two things, adding functions to map and reduce and solving this memory management problem was sort of the main things that Spark did beyond Hadoop MapReduce. And it turns out this particular case, you know, for the types of applications we were talking about, these iterative machine learning algorithms, we were getting, you know, 10 to 100 times speed up over Hadoop. And what was nice about it was, you know, like all engineering projects, you know, it's some combination of cleverness and laziness. And really, out of laziness, we decided we didn't want to innovate in the storage system, right? Hadoop file system was a very nice, scalable system. So Spark was built to run on top of Hadoop file system. So people that were already using Hadoop could basically download Spark, you know, write their program in Spark instead of Hadoop, but they wouldn't have to take all their data out and move it into another system. They could just plunk Spark down on top of their file system and run it and get, you know, 10 or 100 times speed up. So that's why, you know, people started using it, right? Because they didn't have to mess with their data, and it was a lot faster for what they were trying to do. So that's, you know, the memory management part. Now, there's a detail here, which is you might ask, well, okay, that seemed kind of obvious, right? You don't want to have to read the data in if it's already in memory. And you don't want to have to write it out to disk if you know you're going to read it in again in the next step. So you know, you might ask yourself, well, why was Hadoop doing that? And the reason's pretty interesting, is that when Hadoop was built, they had a very demanding design point that they were trying to hit. The idea was they wanted to be able to scale, you know, almost infinitely. And so they wanted to be able to, you know, continue to add machines, you know, to their system as the problem size grew. And in particular, you know, because they were scrappy startup people, they didn't want to have to buy super expensive, well-managed machines. They wanted to be able to just take whatever machines they could get their hands on, throw them in a rack, and use them. And so their assumption was that while you're running a large calculation, the chance that, you know, any one or more of your machines might fail in the middle of that calculation was pretty high, right? As you add more and more unreliable machines, the chance that one of them will fail goes up. And so Hadoop was built in a way that you could recover from partial failures. If a machine goes down during a calculation, it's not a big deal. You can start that calculation up somewhere else. The data is safely on disk, and you can keep going. And so if you're going to try to get rid of all that disk I/O, you need to solve that fault tolerance problem. And Spark did that in a different way. So Spark basically said, I'm going to define this collection type called a resilient, is that right? Resilient distributed data set, right? That is basically just an abstraction of all this distributed storage. They're called RDDs. RDDs, the key thing about them is they're immutable. You're not allowed to update them. So once you've created an RDD, all you can do is apply more transformations to it to create new RDDs. And if you take that step, that makes recovery from a failure much, much easier. Because you don't have to worry. If you have a particular RDD and you've lost a piece of it, you can very quickly figure out exactly what is missing, because you know once it was created, it didn't change. And so what Spark is able to do then, given that, is if you have a statement like this is kind of a simple Spark statement where you're reading data from a file, you're filtering on, you're treating it as lines of text, you're pulling out the lines that contain the word error, and then from those lines, you're pulling out the error message, right? That's kind of what this is saying. You can basically just treat that statement as a recipe for creating any of those RDDs along the way. So this RDD gets created by reading out of the file system. This RDD gets created by applying this function to that RDD. And then this RDD gets created by applying this map function to the data from that RDD. And if you keep track of where all your pieces are in the system, if any one node goes down, you've got the recipe for recreating what was missing. So this is called logical logging. It's another idea that database people have been poking around with for a long time. And if you do it, you can avoid all that disk I/O that Hadoop was doing and solve that performance problem. So it's another case where that kind of thinking got in. I'll just mention briefly another thing that turned out is that, amazingly, a lot of people doing data analysis really were comfortable with SQL, and they liked SQL. And so we had to add SQL to Spark. SQL is the relational database language, if you're not familiar. But everybody in this field has done that. So this is just a partial list of all the big data systems that now have SQL interfaces. And so even though part of this movement, when it started, was called the NoSQL movement, very quickly people realized that for a lot of analytics you want to do, SQL is actually a really nice way to do it. And there's a lot of people who already know how to program it. So it's another place where database thinking came in. Interestingly, a lot of the people using Spark didn't like SQL, and they were more comfortable with languages like R and pandas and systems for doing statistical processing. And it turns out that those languages have a structure called data frames. And a data frame, it turns out, is just a set of rows and columns, very much like a relational data table. Right, so the relational databases are built on this notion of tables. These statistical languages are built on the notion of data frames. But it turns out they're not really that different. They're fundamentally not very different. And so we added in Spark this idea of data frames, which if you read this, and you don't have to, this is basically the first query you learn, the first sophisticated query you learn in SQL is I've got a table of employees and I've got a table of department information, and I want to join them. Right, and so I can put the employees together with the information about their department. That's all this is doing, and it's just written in a different way. And so we built a query optimizer to do this. And I'm sorry, I'm going to skip through this, but again, remember that key thing about database technology where you say what you want, not how to do it. The part that figures out how to do it, the part of the system that figures out how to do it efficiently, is called the query optimizer. So you can build a query optimizer for a system like Spark that takes a high-level description of what you want, compiles that into a program that runs efficiently. So that's what we did. We built an optimizer called Catalyst. And here's what's interesting about it. So this is I took the numbers off because these are old numbers, and they were distracting people. But the basic idea was, you can write in Scala, which is the native language that Spark uses. You can write a program against an RDD, and it'll run at a certain amount of time. We have a Python interface that people like Python. It induces some overhead, but if you like Python, maybe you're willing to pay that. But if you're willing to use the SQL system, there's a bunch of optimizations we do both in the data storage and in the processing that give you much better performance. And you know, this slide is probably almost 2 years old now. It's gotten better and better and better. So the performance boost of using SQL has gotten better relative to the other RDD approaches over time. But what's interesting is, if you don't like SQL, if you're more comfortable with that data frame type of imperative process that you might use with a language like R, you can do it, and you basically still get the same performance. And so the trick is that what the system's doing is it's taking that high-level statement of intent, it's compiling it into an internal representation, and then taking that internal representation and using that to develop an efficient plan to execute. And so what's happening is, whether you write with SQL or with one of these data frame languages, you basically end up with, if you write the same query, you get the same internal representation. That gets optimized the same way, and you get the same performance. And so if you're not a database person, this might not seem very surprising to you, but it is a big deal to be able to get those types of database query optimizations in a language that's not SQL. It's a pretty rare thing to see. So that's why I point that out. OK, good. Oh, boy, I'm going to skip this. Sorry. Oh, no. OK, so good. So where does that get us? And then I want to start looking forward. OK, so where does that get us? So basically, you're able to write a SQL query. So this is saying, I've got a table of tweets, and I'm pulling out the location and the language, and I'm storing that in an RDD. And then I'm going to take that RDD, and I'm going to train a model on it, right? So I'm going to figure out how I can use location to predict language. And then once I've done that, I can apply that in a streaming way. So as new tweets are coming in, I can look at their location and predict their location, their language. Okay? And you know, what's interesting about this, it's not very pretty to look at, but it's all within the same system. It's all within that same framework. So this need that you used to have to bring in one system for machine learning, one system for SQL, a different system for streaming, in Spark, we argue that you don't have to do that. You can do it all in the same program. And that's kind of where that ended up. OK, good. So where we ended up with Spark is there was this inflection point, right? So scale-out processing became more and more important because people were having more and more data. Cloud computing made it possible so that you could run jobs on large computers without having to buy a large computer. You could just rent it for a while. So that really changed things. This thing we're going to come back to in a second of not having to just use relational data, but use lots and lots of different kinds of data became more and more important, and so we were able to support that. This ability to use these different modalities for getting at the data, more and more people wanted to do that. And then, as was mentioned, the fact that all this is happening in the open source made innovation happen faster and faster and faster. And so it was one of these cases where you might wonder, how did a bunch of graduate students in a single lab create software that seems to have had so much impact in the real world? Part of it is they were really good students, but part of it is that it was the right time. This set of things happened, and Spark was kind of there to take advantage of these things as they were happening. So that's just kind of an interesting summary of that. OK, so great. So I try to argue where database thinking helps. OK, so you start off with this low-level MapReduce thing. It's low function. It's hard to use. And you improve it by adding ideas that we've learned over decades of doing big data systems. But not all database thinking is good. And this is the discussion we were just having. So those are the good things I mentioned. But there are some bad things. Database systems, traditionally, they're monolithic, right? And I'll show you what I mean by that in a second. This idea that I mentioned about data, the first thing you do is describe all the data you're ever going to store, and then you can start trying to store it. Adds a lot of friction to the process of trying to collect some data and do something with it. So modern big data systems don't make you do that. They do what's called schema on read, where you basically just store the data, and then when you go to work with it, you try to figure out what's in there. Okay? Which has its problems too, but it cuts down friction for sure. And this is less relevant to the general audience, but database people always say, yeah, we've seen this before, we've done it before. So that's not a helpful attitude for this sort of stuff. That's all. Okay, so that, yeah, that's a little inside baseball kind of. Okay, so here's the main thing. So this is the way database people think about data. Here's my database system. I've got data, I can store data, I can process it, and then I've got this language compiler. Okay, and here's the deal you make if you buy your favorite relational database system or even an open source one. It makes you the following detail. It says, okay, give me your data, right? You're valuable. This data that is what you're going to run your business on that's so important to you, and give it to me. And if you trust me, I'm going to take that data and I'm going to turn it, right, using this nice abstraction into something that you have no idea what it looks like. Okay? I'm going to manage it. And if you let me manage it, I'm going to give you correctness. I'm going to let you run concurrent transactions on it and have that be correct. I'm going to make sure that if you change it, those changes stick around. All sorts of nice things. But the only way you're going to get at that data is if you write in this language that literally you type in all caps. Okay? And the data, no matter what it was, if it was video, if it was images, it was sound, is going to come out as a table. Okay? And if you're willing to make that trade-off, if you're willing to make that deal, I'm going to give you a lot of benefits. Okay? That's the entire database industry is founded on that principle. And let me tell you, you're really happy that your bank bought into that because it gives you a lot of guarantees. But for a lot of things that you want to do, that's not what you want, right? And this is what we're talking about. What you really want is, sometimes you want to run SQL, sometimes you want to run R, sometimes you want to run machine learning. Sometimes you just want to open up a file and run grep on it, right? Or you want to write your own code to do something that these people didn't think that you might want to do. And so what's beautiful about Spark as an example, but all those other systems I showed you as well, is that they kind of organically were built this way so that you're really allowed to come at the data through any of these interfaces you want, including the lowest level, and still make sense of it. And so what that does is it really reduces the friction of, I've got some data, I want to do something with it. Okay? And it lets you collect that data in kind of its native form and then process it. And that, as we were talking about, has had a huge impact on the traction that these systems have gotten. Okay? So this is a place where if you think like a database person, you're not going to come up with a solution. And it's going to keep you from doing things that you might otherwise want to do. Now, there's no panacea. There's a bunch of, like I said, if your bank account was stored in one of these systems, you should be pretty nervous. Okay? Because sometimes they give you the wrong answer. Or sometimes they lose data. But for applications where that's okay, this is useful. Okay? Okay, so how did this play out for Spark? There was a survey done last year of about 1,600 people. What languages do you use when you use Spark? And you can see it's a pretty wide range. And you didn't have to say just one. And I guess the interesting thing is, SQL's going, between 15 and 16, SQL went up a little, R went up a little, Java went down a little. I don't know if they're significant or not. But it seems that maybe the higher level interfaces are becoming more popular. But certainly, lots of people like to access data lots of different ways. This is kind of another view of that. Which components, when you access data, do you use? And you can see there's a pretty wide range. And interestingly, 3/4 of the people who answered the survey said, oh, I use at least 2 of these. I use SQL and graphs. Or I use machine learning and streaming. And fully, almost 2/3 of the people said they use at least 3. So, this idea of multimodal access to data seems to, at least in this, unscientific survey, seems to have some merit. All right. Okay. So now, what's important? So we asked people, what's very important to you about your big data software, and basically said, okay, performance really is important. But after that, I want to be able to do advanced analytics. I want ease of programming. I want to be able to deploy it more easily. And in terms of what's next, I think that's really what's next. So let me just talk about that briefly. So sorry, I already told you all this. Okay, so what's next? All right. So, oh, no, we didn't hear that yesterday, sorry. Okay, so here's what I think's next. We're all interested in data science. I put this up here because in case you haven't seen it, there's been a couple reports coming out of the computer science community that you might want to read about how computer science and data science might fit together. So this is one from the Computing Research Association that you can find. This one is for the National Science Foundation, SCIES, which is the Computer Science Directorate, and called Realizing the Potential of Data Science. And the thing I wanted to talk about is a picture from that, where basically what that report is built around is this idea of a life cycle, of a data science life cycle. That it's not enough just to think about analyzing your data, right, and doing machine learning. But if you think about data science, it's this entire process that starts all the way at the beginning when you're trying to figure out, what questions do you want to answer, what types of predictions do you want to make, through all the horrible work you have to do to clean things, get it into a format where you can make sense of it. Then you get to do analytics and machine learning on it. Then you come up with some insights, and you need to communicate those insights. You need to be able to explain them. You need to understand how robust they are and how correct they might be. And then, there's this idea of data living beyond any one question or application. And so, you have to think about curation and so on. And, of course, there's all feedback loops in here. And so, layered over the top of that, of course, is this, set of concerns around ethics, around privacy, around underlying biases in the data you've collected, around how much can I really trust the insights that are coming out of my analysis. And so, if I look at the future, kind of what I talked about so far was kind of like in this little box here, like how do we make that go faster and maybe be a little more flexible. But there's all this other stuff that needs to be solved if you really want to do data science. And so in terms of what's next, I believe people building big data software need to be thinking about this entire life cycle and how to support it. Okay, and for programs like the program here, that I think is you have a great opportunity to take this more holistic view of using data to solve real problems. And so that, in a nutshell, is kind of the main thing I think we need to be thinking about next. And then I kind of have some details on it. So there's this idea of data wrangling, where you're trying to bring data from multiple sources. You're trying to correct the data that you have because it's missing things. It's got incorrect, it's got corrupted data, and so on. And so there's a huge number of problems here. Database community, among others, have been working on these problems for years and years and years, but they're kind of the wicked problem of data. Just being able to collect data from multiple places and put it together is just something that's done with a lot of spit and baling wire right now, and often doesn't work. And so there's a big need for work there. Okay. This is just one example of some things we've been playing around with, where rather than using people to clean an entire data set, you could give them samples of the data and ask them to clean those samples, and then take what you've learned from cleaning those samples and apply that to the answers that are coming out of the uncleaned data. Kind of the way they fixed the Hubble telescope by putting in a little extra lens to correct for a problem that was there when they put it up. And so that's kind of one idea where statistics and query processing can come together to help improve data cleaning. In terms of ease of deployment and development, this is another place where I think some ideas from the database community can help. So the basic idea is that even if you just focus on that machine learning part of the pipeline, it's very rare that you just take a data set and run one algorithm on it. Okay, I mean, I showed you that on a slide, but that was just an example slide. In general, trying to do analytics is a sequence of steps that you have to go through to be able to make sense of the data. And so I think this is a place where we can use database thinking to come up with a declarative way of specifying what it is that you want to learn from your data, what it is you want to predict, and then having the system be responsible for figuring out what's the most efficient and accurate way for getting you the answer that you've specified. And so we've done some work on that in a project called Keystone ML, where some simple things, if you're a database person, this will look pretty familiar. So you've decided you have this step in your process called where you need a linear solver. Well, it turns out there's dozens of linear solvers out there that have very different performance characteristics depending on the shape of the data you feed them. And so you can have the system automatically pick, based on what the data looks like, which of these instantiations of the solver is the right one for your particular problem. That's something a database system does already for joins, for example. And there's no reason why you can't do that in a machine learning framework as well. The other thing is looking across the whole set of sequences, the whole sequence of operations in a plan. Again, there are things that if you look at the whole plan, you might realize. Like you might realize that the output of this thing gets consumed by 2 different steps, so maybe I should store that in memory somewhere, right? And make those types of optimizations. And so the idea behind Keystone ML, and I'll just build this out, is to try to automate a bunch of those decisions that right now people who are building machine learning pipelines are basically doing by hand. Much like 40 years ago when people started building relational query optimizers, they were basically trying to automate the process of figuring out how to efficiently answer a relational query. So I think a lot of the same insights, obviously different specific techniques, but a lot of the same insights can be applied here. Okay, so that's an idea of deployment. Another idea of deployment is what we did in the Clipper system, which is once you've created a model and you want to use that in an application, as you're getting new data in, you want to be able to keep that model up to date without having to necessarily compute it from scratch again. Because remember, we're talking about big data. These things take a long time. So Clipper is a way of doing incremental maintenance of machine learning models, and then even taking the outputs of multiple different machine learning models and ensembling them in a way to provide a better answer. So, and it's a longer story than I have time to get into now, but the way you might think about abstracting, building this layer is very similar to the way you think about layering, again, a database system where you separate the concerns of the low-level implementation from the higher-level processing. So I think there's some things to be learned there. Okay, so there's issues around curation. There's a lot of things we can leverage in terms of workflows and lineage processing. Happy to talk about some of those. This is just a snapshot for some work we've been doing on image processing for cosmology. This issue that I raised just briefly, but it's a huge issue of understanding the underlying issues with the data that you're dealing with. So there was a feeling that algorithms would be impartial, and that may or may not be true. But if you feed in an impartial algorithm data that was collected with some underlying bias that you don't realize, that bias is going to come through in your analysis. And just trying to understand that and reason about it is something that people really don't know how to do very well right now. Okay, some things around humans in the loop, which I'm going to skip because I want to wrap up. I'll just mention this briefly. I think another thing that's going to happen is that, and you guys are at the forefront of it, so that's why I want to make sure I mention it, is this idea of getting domain people working closely with the people who are building these big data systems so that you end up solving the right problems. And this is something, as I said, in our project, from the beginning we worked closely with people from a bunch of different domains to make sure that what we were doing was actually helpful for them. So it's something I think is really important to do. All right, so just to wrap up, MapReduce was this disruptive technology that has, over the last 10 years, been going through this process of maturing to where now it can solve a lot of the problems that it maybe couldn't have solved 10 years ago. And that, as a database person, I think a lot of the insights that the database community had come up with over the years fit very naturally into this new regime. But there's a lot of focus in those early days on performance and getting things to run fast. That's still important, but I think now as the software is maturing, these other issues are becoming increasingly important. So, dealing with the entire data science lifecycle, trying to make it so that people don't have to understand the details of the system and the details of the data, because they never will, it's too complex. So, automating a lot of that. And this thing about, trying to understand what it means to be making decisions based on data. And how to do that in a safe way. Okay, so I think with that, I'm going to stop, and thank you. you have time for a question? Any questions? Yes.
So one of the problems that traditional database systems solve really well is indexing, right?
Yeah.
So you can perform queries select this, where that, really quick indexing. How do big data systems deal with that? Or do they deal with that?
Yeah, so the question is that one of the big techniques in database systems that I didn't mention is indexes, where if you want direct access to an item, you don't have to look at all the data. You can just follow a data structure directly to what you're looking for. And the question is, how do big data systems deal with that? There's been a number of efforts to add indexing to a bunch of these systems, Spark included. The way you do it is pretty similar to the way you do it in a database system. You just have to be careful that what you're pointing, if you move things around, that the index still points to it. But it's a solvable problem. But what's interesting is that we found that for a lot of analytics applications, you end up not being able to take advantage of indexes anyway. And that's why there hasn't been a huge move to put indexes into these systems, because a lot of what people are using them for seem to not be able to take advantages of indexes the way you want. So I'm sort of giving you both answers. One is you can do it if you want to, but in general, for the types of things people are using these for currently, they haven't really been a huge need for it. There are some details where that's not true. So for example, the graph system we built basically manages its own indexes to be able to let you get at the right parts of the graph. But we don't have a more general index version yet. Yeah.
Following on the last question, indexing and indexes are just one form of metadata.
Yep.
They're the only form, or the primary form, that traditional database management supports. The new environment, we don't yet know all the different forms of metadata, but I'm surprised that the management of and understanding of metadata wasn't part of your new challenge list.
Right. Oh, yep.
So that's the method for increasing or maintaining the performance of your system and abstracting away from the underlying management of the system, the access to it in effective ways.
Yeah. So, the comment and the question was, another major part of database systems is the idea of metadata, which are either structures like indexes that improve performance, or catalog information that tells you what your data looks like. And that wasn't on my list. And I think you're right. I mean, there are actually a number of efforts right now going on and trying to come up with open source ways for doing metadata. There's one at Berkeley that my colleague Joe Hellerstein's doing that seems to be getting a lot of traction. And it was really, I guess, more of just an omission on my part. It's kind of buried in that part on data wrangling, but I didn't call it out as a major thing. But it's
Data wrangling as being the front end.
Yeah.
You go through it. I'm talking about
Yeah.
metadata that's generated as you're doing your analytics, a schema on demand
Yeah.
or on access.
Yeah.
Has
Yeah.
to be preserved somewhere if it's going to be reusable.
right.
That's the point.
So you need to be storing catalogs and that. Yeah,
all
absolutely.
along. And the system has to understand that that's an important part of the data that it's got to manage that's going to be created dynamically.
Right.
Just as you've got streaming and streaming.
So I didn't go into the details, but the Spark SQL system does generate metadata on demand and manages that. But that doesn't get used by some of the other components of the system. Arnie had a question here.
Sure, security seems to be becoming increasingly important. I didn't see any technical ideas mentioned for either scaling on variety for specifying access controls or on implementing it at scale.
Yeah, so security is probably another one that needed to be emphasized more. Again, there were a couple things that were buried there that I skipped over on storing encrypted data. But one of the things that traditional database systems have been better than many other systems, I guess, I won't say great at, but has been access control and managing who gets to see what data and do what with it. And, there's definitely technical challenges with putting that. Those techniques depend on a very strong understanding of the structure of the data. And as you move to this environment where things are a little less constrained, it's not clear how many of those techniques work. Okay, well, you had your hand up, yeah.
Yeah, so the levels of abstraction that have been established in this ecosystem and the delineation between interfaces and so on, is this pretty established and accepted in the community, or are there competing approaches apart from the traditional database?
Yeah, okay, great question. So the question was, I made this argument for this ability of these systems, that these systems allow you to get at the data at different levels of the system. And the question was, are those levels well established, or are there competing proposals for what those levels should be? So it's a really interesting question, because back in the day, people have known about this problem with database systems for a long time, and there have been several attempts in the research community to build various things called extensible databases or things like that, where they pulled out, they basically did that disintegration of the system to allow people to do that. And by and large, those things never caught on. The only thing that ever really caught on was the very low level, the storage level, and Berkeley DB, that Margot Seltzer here is like a great example of that, where people just use that part of the system, even though it's actually just part of a bigger database system. Michael did he do?
There was some transactional database.
Yeah. So, I mean, we can go over what the main projects were, but by and large, those didn't work, and I think it was because of this kind of top-down approach where people were saying, hey, I've got the system, I want to split it into pieces. What's interesting about this world is it grew up the other way. It grew up bottom up. And so people said, we need a scalable file system, and they built one. Oh, we need a scale-out processing engine for that, and we built that. Oh, we need a SQL interface for that, and they built it. So it was a very natural, so every layer got built, not because some architect somewhere thought it might be a good layer to have, but it got built because somebody needed it. And so, so to answer your question, I think in general, most people that work on these systems would draw a diagram with similar layers to what I had, the file system, the processing system, and so on. But, I don't think it's written in stone. I'm sure there are other approaches out there that people are doing.
Okay, just remember these two lines, data acquisition and data integration remain a wicked problem for the people that do homework 1 for data science.
Yeah.
Thank you very much.
All right, thank you.